Okay, so good evening, and we'll start this problem solving session. So today's problem will be based on week 10 content of the week 10 NPTEL lecture videos of the content engineering courses. So the course outline was for this week 10 the content was based on what happens when these zeros are on the right hand side of the this complex plane. So depending on that the presence of the zeros in the either right or the left, we actually divided the systems. We called them as a minimum phase or a non-minimum phase. So as the name suggests, so the minimum phase systems will have the range of this phase plot for that system will be minimum among all the types of plots of the system which have the same magnitude Bode plot. Okay, so that's because of the presence of the right hand side zero, will have the phase range will be different from what it is expected for the non-minimum phase system. Okay, so for the for the minimum phase system. So for the minimum phase system, what happens that when the frequency is very high for the frequency plot, the magnitude plot will be it will be minus 20 dB times the difference between the number of poles and the zeros, right? So when the frequency range is very high, in the log magnitude plot we will have the asymptote plot will be it will have minus 20 dB times the difference between the poles and zero. And similarly in the phase plot, the phase diagram, it will have the phase angle of minus 90 degree times the difference between the pole and zero. So this is because each pole will contribute 90 degree and zero also 90 degree. So the effective contribution will be, as the frequency is very high, will be just the minus 90 degree times the difference between the pole and zero. And similarly in the magnitude plot, because each pole has a contribution of minus 20 dB per decade and zero has a plus 20 dB per decade, so the effective contribution will be just the difference between them. But this is not true for the non-minimum phase system. The magnitude plot will be similar to as a minimum phase system, but the phase plot will be different, right? And then you analyze the idea was to construct the transfer function from a frequency response, right? So it is possible only for minimum phase system. So there is a unique relation between the magnitude and the phase plot for a minimum phase system, right? For non-minimum phase system there is no such relation, and it cannot be determined uniquely from the magnitude plot and the phase plot, right? So for the minimum phase system we can identify the transfer function by simply looking at the Bode plot. So the magnitude Bode plot is enough for that. So we just look for asymptotic Bode plot and the slopes, and from that we can find the corner frequency and also the gain from the initial portion of the Bode plot, right? And then there was also a discussion on the effect of the right half plane zero. So this is for because of the presence of the right half plane zero, so the systems are non-minimum phase system. And for that we see some interesting effect of the zeros, right? Like the undershoot and also talked about the internal instability and the overall stability of the system. So okay, so we'll discuss some basic problem based on this content, and so this problem will be very standard. So okay, so let's discuss this. Okay. So the first question is we are given an closed loop transfer function. So and this alpha is the unknown parameter which is given as a positive. So then the system will be what? Okay, so this idea is again very simple. So as you can see, if alpha is positive, then definitely the zero of the system will be what? So the zero of the system will be, this closed loop system will be the value of the for which the numerator becomes zero, right? So we can see that from this. So the zero will be alpha, right? So we have two zeros there because of this presence of the square. So multiplicity will be 2, and this is positive. So you see that the zeros of the transfer functions are located in the right half plane, and thus the system will be a non-minimum phase system, right? Okay, so based on that, now we have this same transfer function and alpha is positive, then how many zero crossing will occur? Okay, so another interesting phenomena that was observed for right half plane zeros was the zero crossing, right? So for even for this second order system or the higher order systems, okay, so the step response will exhibit such zero crossing, okay, and we know that the number of zero crossing will be equal to the number of right half plane zeros, okay, provided the closed loop poles of the systems are asymptotically stable, right? The closed loop poles will be located in the left hand plane. So first we have to verify whether this systems closed loop system has the poles in the left hand plane, okay. So two ways to verify. So one will be just factorization of this term, so we can just simply factorize this. So we are given 11s plus 6. So this is the characteristic equation, that is the term from the denominator of the closed loop transfer function. So we can just factorize this. So this is equal to this okay, so this is 6 11, so I can write s square plus 5s square plus 5s plus 6s plus 6, right? So I can 6 plus 5 11 and 5 plus 1 is 6, okay. So I can write like this. So I can take common s square from this, so we have s plus 1, this is again 5s I can take common, so it will be s plus 1, and plus 6 I can take common, so s plus 1, so it will be equal to s plus 1 times s square plus 5s plus 6, and again I can factor the quadratic form, this is, so I can factor it as s plus 2 s plus 3, right? So 2 plus 3 will be 5 and 2 3 multiplied will be 6, that is, so this is the factor. So we see that the poles are at minus 1, minus 2 and minus 3. So the system is asymptotically stable for this form, okay, because we know that the transient response, okay, the stability will be determined by the poles, right? It's not depend on the zeros. So from the poles we know that it's asymptotically stable, and for that system if we have right half plane zero, then depending on the number of zeros we will have that number of zero crossing, right? So we have two right half plane zeros because alpha is greater than 0, and this is multiplied with 2, so we will have two zero crossing, right? Also this stability can also be verified by Rao theory also, so you can write this, okay. So the stability for this characteristic equation, okay. So this is 1 11 6 6, so it will be 60 by 6 10 0 and 6, so there is no sign change, so we see that all the poles are located in the left hand plane, right? So this also can be verified. So the system is asymptotically stable, and for that system the number of positive half zeros will determine how many number it will cross the zero. So we have two positive half zeros, so it will cross the zeros. For the unit step response it will cross twice, okay. The zero it will cross two times, right? Okay. Okay, so we move to the next question, okay. So again the same system is given. Now we take this alpha equal to 2, and now we have to find, okay. So another interesting phenomena for this right half plane zero was the undershoot, right? We will observe some kind of like undershoot also, like it will reverse this direction for the unit step, it will reverse the response will reverse the direction, and we will have an undershoot, okay. So usually we have what overshoot, but here because of the presence of this positive half right hand plane zeros, we will have also undershoot. So we want to find at what times this undershoot will occur, okay. So we will have this transfer function. So we will proceed through multiple steps to find this, okay. So first we have to find the response of the system, okay. So for a unit step, so this is step response. So unit step, what will be the response of this closed loop transfer function, okay. So this is easy to find. So we know that if the transfer function is given, that is this form, then we can simply write ys equal to also this transfer function, this one, So this is s minus alpha, so alpha is given 2, so I can directly write also. So s minus 2 square by this form, so that we have already factorized, so this is the factored form of this denominator term, right? So we will substitute for this polynomial, we will just substitute this factor form, that will be easier to solve then. Okay, so we will have s plus 2 and s plus 3 times rs, right? So this is directly follow from this. Okay, so I just multiply this rs on the other side, so then ys, that is the output, will be given then transfer function times this input, and this transfer function, because alpha is 2 and this term I just written in the factor form. Okay, so then for unit step this r will be what? So it will be just 1 by s, right, the Laplace transform. So I can just write it to be s times s plus 1, s plus 2, s plus 3, right? So this is the output that is given for the unit response. Okay, because rs equal to 1 by s for the unit step, right? So then what we will do, we will just find the inverse Laplace transform. So we will write in the time domain, so we can just find the response of the system, of this system that is given for unit step response. Okay, so what will be benefit then, because we want to find the undershoot, right? So undershoot or overshoot means it will be like this, right? So this is the overshoot, okay, or some undershoot will be like this. Okay, so then we see that this is the minimum or the maximum, right? The overshoot will be the maximum point, undershoot will be the minimum point, right? So to find a minimum or maximum of a function will be what? So we will just take the derivative of that function and equate it to 0, then we can find the point at which this minimum or maximum can occur, right? So we have to again verify whether that is a minimum or maximum, because it is the first order condition. Okay, so the first order condition will be what? Just to take the derivative of the function and equate it to find the point where it can have minimum or maximum. Okay, so it can have, it is also possible that that point may not be a minimum or maximum. Okay, so we have to verify that by using the second order condition, that is you have to take the second order derivative. If it is a negative, then it is the maximum point. If it is positive, then it is the minimum point, right? So that's how we are going to proceed. So we will first find the response. So the response will be yt, so that will be this Laplace inverse transform of this ys, right? So it is given in the Laplace domain. We will find the inverse Laplace transform, so it will give us the time domain function. Okay, so then we will take the derivative to find the point where this minimum can occur. Okay, so we will proceed that. So first we will find this inverse Laplace transform of this function, right? So let's do here. So what we have obtained is that ys equal to s minus 2 whole square by s times s plus 1, s plus 2, s plus 3, right? So this is what we have obtained earlier for the step response. This is the response of the system for a step input, right? So to find the Laplace inverse transform, we have to like find it in standard form, so that each standard, for each standard term we know the Laplace transform, we can just find the inverse Laplace transform, right? So we have to find in this form, right? Then for each term, as you can see, we can find inverse Laplace transform easily. So we have to find this coefficient all a, b, c, d. Okay, so this is called partial fraction expansion. Okay, you may have heard. So anyway, we will just proceed step by step. So how to find this coefficient a, b, c, d then? Okay, so we can easily see that this, if these two are equal, then multiplying the factors on the both sides will also keep them equal, right? For example, okay, so first we have to find that we have to find a coefficient of this. Okay, we will just find a, b and c sequentially. Okay, for a, what we will do then, we will just multiply s on the both sides of this above equation. Okay, so then what will happen? Okay, so the idea will be that if the multiplicity is 1 as you can see there is no square term, then we can easily find by multiplying that term on both sides and then taking s equal to 0 for this s equal minus 1, that will make that term 0. Okay, just I will explain this step. So I will multiply s on the both both side of the above equation. So it will be what? If I multiply s on the left hand side, this s will cancel, right? So it will be this term. On the right hand side, this s will cancel, so we will have a term. Other term will be what? bs by s plus 1 cs by s plus 2 plus ds by s plus 3. Okay, so I just multiply, alright. For a term, what will do? Multiply s on both sides. Okay, so I will get this. Then what I will do? I will take s equal to 0 on both sides. Okay, you see that when I take s equal to 0, this term and this term will become 0, right? It will be 0 by 1, 0 by 2, 0 by 3. Okay, so all the term will be 0, only a will be left, right? So you see, we can easily find a then by just evaluating this left hand side term. Okay, we'll just use the same approach for other also. Okay, so when s equal to 0, it will be what? Then minus 2 square by 1 plus 2, 1 multiplied. So this will be 1, this will be 2 and 3, so it will be 4 by 6 or equal to 2 by 3. So we find a equal to 2 by 3. Okay, we will then use this approach for other coefficient also. Okay, so for b, what we will do? Then we will multiply this factor, right? Because then we will have b term there. So multiply both sides by s plus 1 term. Okay, then left hand side will be what? S minus 2 whole square. S will be there, s plus 1 will cancel, so we will have s plus 2 and s plus 3. In the right hand side we will have a into s plus 1 by s, b, c into s plus 1 by s plus 2 plus d into s plus 1 by s plus 3, right? Again we just make s equal to minus 1, so that all this term will be 0, right? Only b will left. So s equal to minus 1. Then in the right hand side what will happen? A, this coefficient with a, c and d will become 0 because of the s plus 1 term. We just make s plus 1 equal to 0. That is what we mean by s equal to minus 1, right? So in the right hand side we will have b. In the left hand side what will be? Then 1 minus 2, it will be minus 1 square. Sorry, taking s equal to minus 1, so it will be minus 1 minus 2, so minus 3 square by minus 1 into 1 into 2, right? S equal to minus 1. So then this implies that b equal to what? We just solve this, so 9 by 2, right? Minus 9 because of this present, so minus 9 by 2. Okay, again we will use the same approach to find c and d. So for c, what we will do? Same. So we will see what is this coefficient, the factor for the c, s plus 2, right? So we will multiply s plus 2 on both sides. Here s plus 2 on the both side, and for d we will multiply s plus 3 on the both side, and then we will make this coefficient, other coefficient 0, right? So the same approach for c, it will do multiply s plus 2 on both sides. Okay, so on the left hand side we will have s plus 1, s plus 3. On the right hand side we will have s plus 2 by s, b, s plus 2 by s plus 1. For c, both term will cancel, s plus 2, so it will have just c, d, s plus 2 by s plus 3. Again we just take s plus 2 equal to 0, which means that s equal to minus 2. Okay, both side. So in this side it will be minus 4 square minus 2 minus 1 1. It will be only c, right? So imply that c equal to 16 by 2, it's 8, right? Similarly d multiply the coefficient, that is the s plus 3 on both sides. So we'll have s minus 2 whole square by s into s plus 1 s plus 2 equal to s. For b, this is s plus 1, c s plus 3 by s plus 2, and d. So again, if we take s equal to minus 3, right hand side will be only d and left hand side will be minus 3 to minus 5 whole square. So minus 3 minus 2 and minus 1. Okay, so d equal to, we find minus 25 by 6, right? So we find all the coefficients. So then using this form, what we have assumed here, this we can write ys directly, right? So then okay, so ys equal to, then a is what we found it, a 2 by 3, so 2 by 3 s. B we find minus 9 by 2, so okay, I'll just write first, then I'll put ABCD value. Okay, that will be easier. So what form we had? A by s plus b by s plus 1 c by s plus 2. This is the form, and we find this ABCD coefficient. So we'll just put them. So it is 2 by 3 s, because a is 2 by 3, b is minus 9 by 2, so minus 9 by 2 s plus 1, c is 8, so plus 8 by s plus 2, and d is minus 25 by 6. So then we take the inverse Laplace transform. So implies that yt will be, then this is, we know inverse Laplace of 1 by s is 1, the unit step, so it's just 2 by 3, and this is minus 9 by 2, so inverse Laplace transform 1 by s plus 1 is e to the power minus t, then 8, this is e to the power minus 2t, minus 25 by 6, this is e to the power minus 3t, right? So this is the response of the system. So, and that is valid for only t greater than 0, right? So to indicate that, we can also multiply with ut also, right? So in some cases you can see multiplication by ut, because this is ut is 0 before t negative value and it's 1 after positive value. So this means also this condition, right? So that you can also omit, indicate explicitly that it's just valid for t greater than 0. Okay, so we have found this yt response. So the next will be then what? To find this minimum or the maximum point. So what we'll do, we'll just take the derivative of this response, okay, and equate it to 0. Then we can solve for the time. The time will give this possible point where this minimum or the maximum can occur. Okay, so the question was initially to find the undershoot. Undershoot means it should reach the minimum point, right? So for that we found first this response yt. Now we will take the derivative of this. So y dash t, we compute it. So simply 9 by 2 e to the power minus t minus 16 e to the power minus 2t minus minus plus 75 by 6, or you can just simplify it. 6 means 25 by 2, right? E to the power minus 3t. So this is the derivative of the function. Okay, so we equate it to 0 to solve for the time. So how can we solve? Because we have e to power minus t term. So what we will do, first we will multiply e to power 2t on both sides. Okay, so just multiply e to power 3t we will multiply. So then the first term will be what, 9 by 2. So this is positive term, so we can multiply on both sides, right? So e to the power 2t minus 16 e to the power t plus 25 by 2 equal to 0. Okay, now take x equal to e to the power t. So this equation will then become what? It will be 9 by 2 x square minus 16x plus 25 by 2 equal to 0. Okay, so we have a quadratic equation which we can solve for x. Okay, so x which is equal to also e to the power t will then be what? Just we solve this using calculator. So these values are 2.3964 and 1.5 1.15914. okay, so this solution of this quadratic equation are this, which is also equal to e to the power t. So t will be then what? This ln of these solutions, right? This ln of this value, and that will give this two t values. Okay, so that is ln of you can write x. Okay, because these are x value. So this actually gives the two values of t. So one is 0.874 and another is 0.147. okay, then we have to verify out of these two values which one actually gives this undershoot, that means the minimum value. So what we will do, we will take the second derivative of y, and if it is negative then it is the maximum point, and it is, if the second derivative is positive, then the t value will give the minimum point, right? So second derivative you can compute from this. So it is minus 9 by 2 e to the power minus t. So plus 32 e to the power minus 2t okay, then we have minus 25 into 3 by 2 e to the power minus 3t. Then we use the both the t values there and we will check. Okay, so we find that, okay, we'll just put first value 874 and it comes to be 0.9695. okay, so positive number. And if we put the second value, that is this one, 0.147, so it is approximately minus 4.135. so you see that this point is the minimum point and this is the maximum. So this corresponds to undershoot. Okay, because we need undershoot, right? So this corresponds to the undershoot point and this corresponds to the overshoot point, maximum value. Okay, we need this. So we see that this is the solution, that is at this time 0.874 we will have this undershoot in this response. Okay, so okay, just to recollect, this idea is very simple. So what we will do, we will just find the response of the system. So the response of the system for a unit step, we can easily find that and take the inverse Laplace transform. So we just had this partial fraction expansion just to find this inverse Laplace transform and nothing else. So once we have this inverse Laplace transform, we know the response of the system, and once we have the response of the system, we can find its minimum or maximum value, because we know that the minimum or maximum can occur at the, if the derivative is 0, first order derivative is 0. So from that we can find this solution, that is time at which the minimum or the maximum can occur. Then we have to verify whether that point is a minimum or maximum. So that can be verified by the second derivative, right? So that is second derivative, and if it is positive, then that point will be, at that time will be minimum will occur, or minimum, or in this case this is the undershoot, right? Okay, so again the same question, we have this alpha equal to 2, then we have to find what is this magnitude at this undershoot point. Okay, so again, so this is just direct now. because we already computed the response. So what we have computed, this response is yt equal to this one, the response we computed here. So using all the previous step, we have the computed, this is the response, right, for alpha equal to 2, and if the input is given as a step input, then this is the response. So we'll just copy this. So this is 2y3 minus 9 by 2 plus 8 minus 25 by 6 minus 3t, right? So as you can see, this is the response. Also you can also like check whether this is correct or not also. Okay, so one thing I can mention here, because of this factorization, right, this, so your poles will be what, like you should have a response like for s it will be constant term, for s plus 1 you should have a response like e to power minus 1 like minus t, for this e to power minus 2t and e to power minus 3t, right? This is Laplace inverse transform. So you can see that is what we got also in the response, right? One constant term, one term with e to power minus t, so that correspond to the pole at the minus 1, this correspond to the pole at the minus 2, this correspond to the pole at the minus 3. So it is also one way to verify whether you have obtained the correct answer or not. Okay, only this coefficient will be determined by the zeros, right, and the term that is present in the numerator, as you can see here. So this term will determine this coefficient value ABCD. That's how we computed. Other term will determine the transient response, like this pole. That is also evident from this response, right? Because of the presence of the pole, we will have this kind of terms. Where this pole is located, we will have the exponential term, and if it is a complex conjugate, then we will have like sine or cosine term, right? So for this real part, we will have this response. Okay, so anyway, we have already computed this is the response, and we already also computed the point where this undershoot happens. So this one like 0.874. okay, so we know that this is the response and this is the time at which this undershoot occurs. Then we can just compute this magnitude at this point, right? So this is will be we just substitute that value at which this undershoot occurs, then that will give this magnitude value. So we'll just put that value 4 plus 8 e to the power minus 2 times 847 minus 25 by 6 e to the power minus 3 times 0.847, and we just compute it, and it comes around minus 0.121. okay, so this is the value of the undershoot. So this is the correct answer. So one thing you have to notice is the negative sign here. Okay, so that is because of the presence of this right half 0, the response will be something like that, right? So it will just initially some direction, then it will come, and then it will just follow that response. Okay, this undershoot. So you can see it will be some negative value, right? It will be below that 0 because of this 0 crossing. We also have already seen that in the second question. Okay, number of 0 crossing, right? 2 0 crossing. So this response will be something like that. Okay, you can just use this function and plot. Okay, because we already have this response, you can plot in the MATLAB and see. So this will be some kind of response there. Okay, so it will start from that, and you will see that there are 2 0 crossing. Okay, so 2 0 crossing will be there because of this 2 right hand side 0 present, and this will be undershoot. So this point we computed this time, so we just substitute that and we will find that this undershoot value, and that value we see that because of this 0 crossing it will be in the negative side, and this will just give us a negative value, and thus we also call this a undershoot. Okay, so so then we have already found this magnitude of this response. Okay, so again we will consider this same system. Alpha is also given 2 for this, and we want to find the steady state output of this system for this unit step response. Okay, so what we will do, again we can use directly this response because we already computed the response. Then for steady state, that means t should be very high, right? It should be like steady state means when the transient response should die out. What is this steady state value, right? So transient response should die as the time goes to very high value or infinity, then the transient response will die. So again we just write this response what we have found earlier. So this one 2/3 minus 9/2 minus 25/6. Okay, so we are given this time response. So as you can see, as the time will become very high, that is it will go to infinity, for high value of t, this and this term will decay, right? It will decay to 0. Only excluding that first term, all the terms will decay to 0, right? So these are due to the presence of this right half plane, because I can also write this also like this, right? So we have factorized this term as this. So due to the presence of this left half plane poles, we have this kind of coefficient here that will decay. That also follows from the stability of the system, because of these poles are present in the left hand plane, so they must decay. They should not contribute to the steady state response, right? So they only contribute to the transient response, how that behaves. So as time goes to infinity, all these terms will decay. So only we are left with y t, okay, value 3. For t very high value we have this is, so it is equal to this. So this is the steady state output of the system. Okay, for this system, when we give this unit step input, so the response will be like this, and the steady state will be after that decaying, all this transient response has died out, that is when t goes to very high value, all this term will decay. So only we are left with this first term, and that will give the steady state response, right? Okay, so next then we move to the next set of question. So this will be like the determination of the transfer function. Okay, for the system, we don't know the physical or mathematical model of the system, we just know the frequency response. So we will be dealing with minimum phase system. So we just need only the magnitude plot, that will be enough to determine the transfer function. So this is the experimental determination of the transfer function, and we are given the Bode plot. So this is just the asymptotic plot. So from that asymptotic plot, we see that initially it has minus 40 dB per decade slope. Then at omega 1 frequency, it changes from minus 40 dB to minus 20 dB per decade. Okay, and then at the frequency of omega 2, it again changes from minus 20 dB per decade to minus 40 dB per decade. Okay, so very simple Bode plot. So we can see that then this is one corner frequency omega 1, where there is a change of slope, and at omega 2 there is another change of slope. So this will be another corner frequency. And from the change of the slope, we can identify whether this corner frequency corresponds to a 0 or pole. So initially from minus 40 dB per decade, there is change to minus 20 dB per decade. So the change is 20 dB per decade, right? Positive change. So that will be contributed by a 0. So this omega 1 will be 0 point. So it will correspond to this 0, this corner frequency. And at the second corner frequency omega 2, the slope from minus 20 dB per decade, it changes to minus 40 dB per decade. So there is change of minus 20 dB, that is minus 20 dB per decade. So that will be contributed by a pole. So this omega 2 corner frequency will correspond to a pole, right? So we know that there is one 0 will be located at that point, and one pole will be located at this corner frequency, that will correspond to this corner frequency. And from this initial part, we can find like how many poles are there at the origin or the type of the system, right? So if it is a initial line is a horizontal line, that means a type 0 system, there are no poles at the origin. If the slope is minus 20 dB per decade, then one pole, minus 40 dB per decade, then two poles, that is the type 2, and so on. So depending on the how much it is multiple of minus 20 dB, in the initial slope, we know that number of poles are located at the origin, or that will correspond to the type of the system. So for this we have minus 40 dB per decade initial slope, so that will correspond to 2 poles at the origin, right? So the form can be guessed to be like this form for this transfer function, that is because of the initial minus 40 dB per decade, so we must have 2 poles at the origin and one corner frequency, that is positive 20 dB decade or dB per decade change, so that corresponds to the 1 0, and another point, another corner frequency we have minus 20 dB per decade change, so that will correspond to another pole. Okay, so if there is changes of minus 40 dB per decade, then that will correspond to second order system, right? The second order component of that system, that is we have a quadratic coefficient there, right? So we don't have in this case we don't have such term, so we will have only first order terms, right? This corresponds to 0. Okay, so now we will just determine all these terms. Okay, the unknown are this a, b and k. Once that are determined, then we know the overall transfer function of the system, right? Okay, so first we will find the value of the a. So how will we find? So first observe that as discussed, this omega 1 correspond to 0 because of this positive change, right? From minus 40 dB per decade it changed to minus 20 dB per decade. So the contribution at this point was 20 dB per decade, so that is contribution by a 0. So this omega 1 will related to that a point, right? So let's find then. Okay, so how will find? So we see that this slope is minus 20 dB per decade, okay, at this point. And if we know the slope and these 2 points, then we can just write the slope also like this, right? So one thing to that, this is a log scale, so all these values will be in the log of that frequency, right? So this point will correspond to the log of omega 1, this will correspond to the log of 1, right? This point, because this is a log scale, right? So these values are in the log format, and this slope is minus 20 dB per decade. So we can find this slope is what, minus 20, and at this point this value is 20, so y value is 20 here, and at this point this y value will be 0, right? Y means if you consider this line, this straight line, so this is like this plot, right? So let this be x and this is y, then y changes from 20 to 0 there, and this x changes from log of omega 1 to log of 1, right, at this point. Okay, so if we know these 2 points and this y value at that point, we can easily compute this slope, right? So this will be this y difference minus x difference, that is the slope, right, of that line. So this y difference is what? We see that it's 20 at point and another point is 0, so we have 20 minus 0, and this corresponding x difference will be what? This one, log of omega 1 minus log of 1, right? So then we just simplify this, so it is equal to 20 by log of omega 1 minus log of 0 is log of 1 is 0, so this is just log of 1 is 0. Okay, so then we have log omega 1 equal to then minus 1, so then omega 1 correspond to what? Then this is that 10 to the power minus 1 is equal to 0.1. okay, so this is omega 1, and that will also correspond to the a value. Okay, so because your transfer function will be what, like this, right? This corner frequency. So okay, so first write this in the standard form, then it will be easier understand. So for the border plot, what we will do, we write in the standard form, right? So standard form means all this term will be okay, so this is like this term, right? So k time ts plus 1 and t1 and t2s plus 1, like this, k dash. Okay, so this is standard form, okay, where the time factors are multiplied with the s and the other term will be 1. Okay, so that can be easily transformed. So we'll just divide a on the numerator and b in the denominator. So we will have s by a plus 1. So it will, and this is s square s by b plus 1. Okay, so will be s plus a. So to cancel it, we need a. Okay, and b, right? So let's omit this. So equal to k dash times s by a plus 1 by s square s plus b plus 1. Okay, so this k dash is जो है k a by b. Okay. Anyway, so this is the standard form. We wrote this. Then we can find that this corresponds to the corner frequency, right? Omega 1. So this is what we obtained there, omega 1, that is a value. Okay. Similarly, to find this b, we have to find this second corner frequency, right? And you see that this second corner frequency corresponds to the pole. Then again we will find. So again we consider this portion of the line. So this portion. Yeah. Okay, so this portion of the line, the slope is again minus 20 dB per decade. But these 2 points are, x point are what? 1 and this omega 2, and corresponding y point are 0 and a minus 20. Okay, again we just use this slope formula. So again we have slope is minus 20, because this slope is minus 20 per dB per decade in this region. Okay, and these two y point are 0 and minus 20. So 0 minus 20, and corresponding x values are, one is 1, another is omega 2, and because of the log we will take log of that. Okay, so 1 is log omega 2. Okay, it is 0, sorry, log omega, it is 0 point, it is log 1, right? So for 0 the corresponding x value is log 1 for 0, and for 20 it is omega 2. Yeah, minus 20 it is omega 2. Okay, so it will be minus 20, so minus minus plus, right? Okay, so just verify this 0 and minus 20. So we have 0 minus of minus 20, so plus 20, and the corresponding values are 1 and omega 2, right? So again we just simplify that. Again log of 1 is 0, so it will be minus 20 by log of omega 2, or log of omega 2 equal to 1. That means omega 2 equal to 10 to the power 1 equal to 1, right? Sorry, 10 to the power 1 equal to this 10. So we find this omega 2 is, this one is 10 radian per second, and that also corresponds to the b value, right? Okay, so next question will be finding that k value again. Okay, so first note that this is what the k value is given, and we can find this k value for this in the standard form. Okay, so this is k dash correspond to. Okay, so what we are going to find is k dash first, then because k dash is related to k this, so in that way we can find that k value. Okay, so just first find this k dash value. So how to find that k dash value? So so if you remember, okay, for type 2 system, so initial slope will be what? Minus 40 dB per decade, right? This is the initial slope, and then it may, the Bode plot may change something like that, or something it will change. But when determining the error constant, you know that if we extend it and intersect with the 0 dB line, or when this magnitude is 1, that frequency will be numerically equal to the root k value, right? So for this our case it is k dash. Okay, in the standard form is k dash. Okay, so not to to avoid the confusion, I have denoted it to k dash. Okay, so so the k dash will be the point, the square root of this k dash will be the point at which this, the frequency at which this initial minus 40 dB per decade line will intersect. Okay, so in our plot, okay, we'll just extend it, so it will intersect at this some point. So let's denote it to be omega 3. So we have to find this omega 3. So omega 3 will be then equal to root over of the k dash, right, k prime, because of the standard form this. Okay, so once we find this omega 3, we can find this k dash, and from that we can find this k value. Okay, so that is easy. So how to find this omega 3? Again, we just consider this line minus 40 dB per decade, that is what going to intersect on the 0 dB line. Okay, so for that we will write that slope equation again. Okay, so let's just write. Okay, so for this case our slope is minus 40 dB per decade. Okay, as you can see this red line, so it is minus 40 dB per decade, what we have extended to intersect with the 0 dB line, and one point, this is 20, 0, and corresponding are log omega 1 and log omega 3, right? So we'll just write that. So minus 40 dB per decade, that is slope, which also we can compute by 20 minus 0 and corresponding log omega 1 minus log omega 3. Okay, this is what, so 20 minus 0 here, and this corresponding are log omega 1, and this is log, sorry, this line, so 20 and 0, the red line. So 20 and 0 are the y point, and the x point are corresponding x point are log omega 1 and log omega 3, and log omega 1 we already computed omega 1.1, so we'll substitute that. So 20 by log 0.1 minus log this is omega 3 that we want to compute. Okay, so we can write it log 0.1 minus log omega 3 equal to minus half, right? So 20 by minus 40 minus half, now reply that log omega 3 equal to log 0.1 minus half. So log 0.1, let's just compute it. Okay, so this is minus, so this is plus, right? Half will go there. So log 0.1 is minus 1 plus half, so it is minus half. Okay, so also omega 3 is what, square root of this k, right? So we'll just write that. Okay, so log square root of k equal to minus half, that is what we obtain there. So k prime, yes. Okay, because we have denoted k prime, right? So then you see that. Okay, I can take this square root outside, so it will be log k prime equal to minus half, or k prime equal to just write this. Okay, log k prime equal to minus 1. Okay, which implies that k prime should be 0.1. Okay, so this square root I can take outside as a half, so I can solve this, or you can just solve also for square root of k first, then also take the square of that, and because you can also solve like this, k prime equal to 10 to the power minus half, then we take the square on both side and we get that also, right? Then also minus half to, so it is 10 to the power minus 1, that is what, 0.1 we obtain k prime. Okay, so once we obtain k prime, we know that k prime is related to k how, ka by b, right? So it is ka by b, and implies that 0.1 equal to k A we obtain 0.1, B is 10, reply that K equal to 10, right? This is the correct answer. Okay, so then we can write the overall transfer function also, because our assumed form was like this. So we just substitute all the values, then the transfer function will be 1. So we have assumed K s plus A by s square s plus B. So just substitute all these value, 0.1 by square s plus 10. So this is the transfer function that is obtained from that magnitude Bode plot, right? Just using all this value we obtain that transfer function. Okay, so next we will consider a simple question where you see that we have a plant, controller and a sensor that actually gives this feedback loop through the sensor. Okay, so we see that our plant has a right half plane 0, also this controller also has a right half plane 0, and we see that because of this zeros are at the same point, the right hand 0, because of this cascade we can have this cancellation, and we can through this cancellation can we have like stability for the system. And what will be the issue when we have this type of exact cancellation? So you already have seen this in the lecture video. What is the issues of this exact cancellation? That is, if you have a right half plane 0, you cannot cancel it with a right half plane poles and vice versa, right? It will have some issue. So we'll just see through this example what issues it can have. Okay, so first we see that we have this transfer function given for this control and plant. So through this pole and 0 cancellation, so we just assume it is a valid operation. Okay, so the closed system, what will be the closed system? Okay, so whether it is stable or not, we will determine that. Okay, so how to find that? So the thing is that we are asked about the closed loop system, so we will determine this closed loop transfer function. Okay, so let denote G to be GC times GP. Okay, so this is the two cascade one. So then our system will be in the standard form, right? This G, this output, so this is H, and we have this. So then overall transfer function will be what? It will be G by 1 plus GH, right? So this is the overall transfer function. So G is equal to this. So we can easily find this overall transfer function or the transfer function of the closed loop system. Okay, so first we will find this G value. So G equal to GC into GP. So these two terms. So these two terms means we have 8 s plus 5. Okay. And this is 0.5 s minus 2 s plus 4, right? So we see that the pole and 0 cancellation, and it is simply s plus 5 by s into s plus 4. Okay, so then the closed loop transfer function will be what? So it is just G by 1 plus GH, and H is 1 for our case now. So we have 4 s plus 5 by s into s plus 4 by 1 plus 4 s plus 5 by s into s plus 4, right? Okay, so just simplify this. So it will be 4 s plus 5 by s into s plus 4 by s into s plus 4 plus 4 s plus 5 by s into s plus 4. So these two terms will cancel. So we'll have 4 s plus 5 by s square plus 4s plus 4s plus 20 are equal to 4s plus 5 by s square plus 8s plus 20. So we have to verify whether the poles are in the left hand plane, then the system will be stable. So s square plus 8s plus 20, I can just write it to be s square plus 8s plus 16 plus 4, that means s plus 4 whole square plus 2 square. Okay, so we see that the poles will be then at what, minus 4 plus minus 2j, right? Just equating that equal to 0. Okay, if we equate equal to 0, then we find this as the pole, right? So you see that poles are in the left hand side, right? These are complex conjugate poles which are located in the minus 4, and this is 2j and minus 2j. Okay, these are the poles in the left hand side of the plane, so the system is actually stable. Okay, if this cancellation of pole and 0 we take it is a valid operation, then we see that our system is actually stable. Okay, so in the lecture video we already have like you have already seen like the issues of this, right? Because there could be slight changes in the system poles, and then we may not have this cancellation, and that will result in the instability. So another issue will be like internal stability of the system. So whether this system is stable or not internally, so we want to also find. So for that we'll see that, okay, so this response u so what we will find is the signal at this point. So the transfer function from this r to u. Okay, so this is an internal signal, and we will see whether the transfer function from this r to u, the closed loop transfer function, whether that actually result that transfer function is stable or not. Okay, that means for that transfer function whether the all the poles are located in the left hand plane or not. Okay, so what we will find, so we will find u by r. Okay, this one. Okay, so we can rewrite this transfer function, okay, for r as an input and y as an output. Okay, so how we will do, so this will be what, this is, okay, so this is gc there, so we have r here, rs, and this is us. Okay, so we will take us as the output now and redraw the transfer function. So this is 1 there, and this is gp, okay, and this is plus minus. Okay, we have just redrawn that transfer function. We have taken this as an output and we put this plant and 1 as the feedback now. Okay, so to find the transfer function from r to u. Okay, so this is what we have done. Okay, so now this will correspond to the h part and this is the g part. So the closed loop transfer function will be what then, between u and r, it will be gc by 1 plus gp gc, right? So this is correspond to g part and this is the correspond to h part. So again we apply this formula. So this g will be gc and gc times this h will be gp, right? So this is what we obtain, the transfer function. So we just substitute this gc value and gp value and see. Okay, gc value is 8 plus 8 times s plus 5 by s into s minus 2, right? By s into s minus 2. Okay, and this is 8 into s plus 5 by s into s minus 2. Okay, anyway we have computed gp into gc, right? So we can use directly this for, okay, so we have computed gc into gp, so it is already computed 4 times s plus 5 by s times s plus 4. Okay, so we already computed that here, so we will just substitute there for this term. So 4 into s plus 5 by s into s plus 4. Then we just simplify that. So we have 8 into s plus 5 by s into s minus 2 by s into s plus 4 into s plus 5 divided by s into s plus 4. So now you see that only this s term will cancel, other terms will not cancel. So this will 8 into s plus 5 times s plus 4 by this term we computed here. So this is exactly this term, right? So s square plus 8s plus 20. So this term, so s square plus 8s plus 20. Okay, so this term is this one, the other term is this one, like s minus 2. We have to multiply that also. So you see that, so this we already computed, the poles are at -4 plus minus 2 here, right? But for this you see that pole is at 2, right? So you see that for this internal signal here, if we compute the transfer function, then it has a right half plane pole, right, 2. So this internal system is not stable, right? Even though we assume a perfect pole and zero cancellation, okay, so we assume a perfect pole and zero cancellation of this right half plane 0 and pole, and we find that the overall transfer function can be stable there if this perfect pole zero cancellation occur. The presence of this right half plane 0 or pole will make this system internally unstable, right? That is what we observed here. We computed this signal y, this transfer function from r to y, u, this internal signal u, and we see that this term appears there, right? So that will contribute a positive side 0. That means the system, positive side pole. That means this system is not internally stable, right? So you see that there is some issue, and for that we cannot cancel and right half plane 0 with a right half plane poles by placing exactly at that point the right half plane pole, or vice versa, right? Even if this exact cancellation will occur and the system will be stable, overall system will be stable, okay, the internal system will be unstable, okay. So this perfect cancellation may not also occur in the real life, because of this, because you want to realize them physically, right, all these terms. And after realizing this physically, you may observe that this 0 may be at some point like 2.202 or 1.98 or 97, like that, instead of exact at the 2. Then we say that this exact cancellation may not occur, okay. Or if the system parameter changes, like for aging or some effect, like after some time or something, then this pole location will change, right? Because this physical system will change somehow, effect of temperature or the environment or something. So for the plant also, that is also applicable. For plant also, this pole location will change. So then you see that then also this exact cancellation will not occur. So it's not an option, like it's not a good option to cancel this right half plane 0 or poles by placing them like in a cascade, right? Okay, so okay, so that's all. So these are the problems that we'll discuss, okay. So if you have any doubt, you can ask, okay, regarding any problem or any doubt also, okay. Okay, so if you have no doubt, then okay, we can close this session, and we'll meet next week, okay. Thank you.